Now let's study about a theorem called as work kinetic energy theorem. This theorem will give a relation between work and kinetic energy. Let's see now how they are related to each other. So for that, let's take an object here. Okay. Let this be a flat surface. On this flat surface, we take an object of mass m, and then we give a force here. The force, let the force be F. Okay. So when you give a force, what happens? The object will start moving. It moves from here to here. It moves a distance or displacement of the object will be S. Okay. So we know that work is equal to force into displacement. Okay. So work W is equal to force, that is F, into displacement is S. Okay. Let this be equation 1. Next, what we do, we know the formula for force. Okay. Force F is equal to mass into acceleration from Newton's second law. Okay. Force is equal to mass into acceleration. Let this be equation 2. Now what we'll do, we'll take the equations of motion. Okay. So in the equation of motion, we have something called third equation of motion. Okay. Let's use the third equation of motion. So using the third equation of motion, use the third equation of motion. So third equation of motion, if you see that it's v square is equal to u square plus 2a. Yes, there are different ways of writing it. One of the ways is this one. Now our aim is to find what is a here, acceleration. So what I'll do, I'll take this u square to left side. It will become as minus u square. So we get here v square minus u square is equal to 2a. Yes. From this, what is a equal to? So bring the 2 and s down. So we get here v square minus u square by 2s is equal to a. So this is the value for acceleration. Okay. So let this be equation 3 here. Okay. Now what we do is we take equation 3, okay, the value of acceleration, substitute in equation 2. So substitute value of a, okay, the acceleration, in equation 2. So instead of writing f is equal to ma, you substitute the value of this one. So what we get is f is equal to m mass into, instead of acceleration we got here, that is v square minus u square by 2s. So v square minus u square by 2s. Okay, so this we get here. Now what I'll do is, let this equation be, say this 3, this equation be 4 here. Okay. Now we take equation 4 and substitute in equation 1. Okay. Because our aim is to see what is the formula for work here. Okay. So substitute equation 4 in equation 1. So substitute equation 4 in equation 1. Let's substitute and see. So what we get is W, work, is equal to force. No, force is here. Instead of force, we get this quantity, that is m into v square minus u square by 2s. Okay. Into, we see this s is there now. So right here s here. So here you can see s and s will cancel. So what we left with m into v square minus u square by 2. So now what I'll do, I'll multiply the m inside here. Okay. Like this way, m into v square minus m into u square. So we get here m v square minus m u square by 2. This you can write separately. That will be m v square by 2 minus m u square by 2. Okay. So we know kinetic energy. What is the form for kinetic energy? It's half m v square. So this you can see m v square, and this is m u square. This you can write as the final kinetic energy. Okay. That is kf minus this mu is 0. That's u stands for initial velocity. This means the initial kinetic energy. So ki. So there's a difference in kinetic energy. Final kinetic energy minus the initial kinetic energy. That you can write as delta k. Okay. Ke you can write also now. That's kinetic energy. Okay. And left side what we have is, left side we have here work. You can see that work is there. So right here work here. So we can say that work is equal to the change in kinetic energy, or work will cause a change in kinetic energy. Okay. So if you do some work, the kinetic energy of the object will change. Okay. So this is about the relation between work and kinetic energy. This is a very important relation. Okay. Next, what we'll do, we'll see some special case here. Okay. Let me erase the left side and see a special case here. Okay. You can write up to here. Then I'll erase the left side. We'll continue from that side. Okay. So there's some special case here. The first special case is, if work is positive, kinetic energy also will increase. Okay. So first one, if work, the work done, see here work is positive, work done is positive, the kinetic energy of the object will increase. Okay. This symbol I written as increasing for increase, okay, to show increases. Then second one is if work done is negative. Okay, work done is negative. We do negative work means the kinetic energy of the object will decrease here. Okay, so decreasing I written like this way. We can write in words also. The third condition is suppose you don't do any work. No work is done on the object. Say for example, no work is done on the duster. So if work done is equal to 0, what will happen to kinetic energy? Kinetic energy will be constant here. In this case, the kinetic energy is a constant. Okay, there is no change in kinetic energy. That means the object will go on with the same speed. Okay, that you can write here. The object moves with a constant speed. Okay. The object moves with a constant speed. Okay. So these are three special cases here. So the important relation is work is equal to change in kinetic energy, or work will cause a change in kinetic energy. So this is about the work kinetic energy theorem. It's a very, very important theorem here. Thank you for watching.